ഇന്നലെ പ്രിയ ടീച്ചറെ സിസ്റ്റം എടുത്തേ നമ്മള്. പ്രിയയുടെ ലാപ്ടോപ്പ് എടുത്താലെന്നാല് ഇതിലും പ്രശ്നമല്ലേ?
ഒന്നേ വർക്ക് ചെയ്യുന്ന മോശം, സ്വിച്ച് എല്ലാം കംപ്ലൈന്റ്.
ചേട്ടാ ഇതൊന്ന് പ്രിയയുടെ സിസ്റ്റം അയാളെ കണക്ട് ചെയ്തോ. ഇത് എടുത്തോ പൂരണ്ട എത്തും. അല്ല അത് എടുക്കണ്ടത്.
അത് വർക്കിംഗ് ഓക്കെ മോശം.
ഇപ്പൊ വരുന്ന അറിയില്ല. ഈ ക്യാമറയാണോ ആ ക്യാമറ? അല്ല ആ ക്യാമറ എടുക്കുന്നു. സർ മൈക്ക് ഓൺ സർ.
Good morning to all. So we gathered here to distribute certificates to the institution and to the students who completed the course of space program. So as part of the World Space Week 2023, the Department of Physics, Mahatma Gandhi Government Arts College is conducting several programs, painting competitions, and again we are going to conduct a tour also, educational tour to planetarium, and we are also going to conduct one national program next week. Our college is recognized as nodal center to conduct various programs on space. And we are fortunate to have our faculty, one of our faculties who is specialized in astrophysics, Dr. Priya Bharali is the coordinator of this program. As part of this, we conducted one course from 20th July to 4th August 2023, and several students have successfully completed this course, and we are going to distribute certificates to the successful candidates. And our college also got an institutional certificate, and the course is conducted in future also. This is the beginning only, start. This is the starting, and we will conduct every time whenever the ISRO offers the course. Again, it will be conducted. Final year students of maths, physics, chemistry, and computer science are eligible, not only of our college, even from outside also. Undergraduate and postgraduate students of final year from departments of maths, physics, chemistry, and computer science are eligible, so they can participate in this program. And I thank our colleagues, my colleague Dr. Priya Bharali, as well as our colleagues Dr. Satish, Sandeep, to successfully complete this program, and I hope they will cooperate in future also to conduct many such programs. So to celebrate this valedictory function for ISRO Start program, I welcome our principal, respected principal, Dr. Asif sir. I'm extending warm welcome to our principal. I welcome Dr. Gopinathan sir, so coordinator IQAC, Mahe, our college. I welcome Dr. Manjunath sir, head of the Department of Chemistry. So I also welcome staff from the office, Sajeev Kumar sir, superintendent, Girish. So I also thank all the students who participated in this program. I welcome all the students. I also welcome faculties from other departments. Say in the department, Manju madam, Radhika madam, even students from other departments. I welcome all of you. To start this program, I request principal to give a brief speech.
Morning. Respected colleagues, my dear students, it gives me immense pleasure to learn that physics department is going to conduct several programs in connection with World Space Week. And it's also a happy thing that our institution has been recognized as a nodal center for ISRO, and we have got a certificate. And some of our students have also undergone some courses. And I congratulate all the students who have won the certificates, and I also congratulate the coordinator, Dr. Priya Bharali. And our physics department has been in the forefront of conducting programs, under this Dr. Mr. Shankaracharya sir and Dr. Satish and Mr. Samhid and Dr. Priya Bharali. All of them have been involved in a lot of research activities, and also they have been conducting or organizing programs like this. And last year, Dr. Satish he had organized a seminar, and this year, Dr. Priya is the coordinator. And I am sure that in future these activities will continue, and it will gain momentum, and it will be what you call an incentive to research programs and also. So I don't want to take much time. I once again congratulate Dr. Priya and all the members of the physics department. And I don't want to stand between the speaker, because she's going to deliver a lecture in connection with the World Space Week. And I don't want to speak much. I don't want to take much of a time. So thank you, one and all. Thank you very much.
I requested Dr. K. Gopinathan sir, coordinator accuracy cell, to say a few words.
Respected Principal, Dr. C. Asif sir, Senior Faculty Member, Dr. Manjuna sir, Head of the Department of Physics, Shankaracharya sir, young vibrant faculty members of Physics, Dr. Priya Bharali, Sandeep, Dr. Satish, all are very good in research and doing good work to our college, especially for youngsters, and other staff members from office and other faculty members from other departments, my dear students. It is nice to hear that our students are somehow they are getting mingled with or getting connected with the space program of our country, which is fast growing. World Space Week 2023, the theme is space and entrepreneurship. Now, it is one of the very prominent field that entrepreneurship is going to highest standards. Especially, ISRO is getting huge amount of money from other countries by sending satellites, and they are sparing this bandwidth from other communication satellites. So there is a lot of scope and opportunity in various fields, not only in directly related with that Priya Bharali may be speaking all these things. There lot of opportunities are there, directly or indirectly connected with. You need not get enter into ISRO directly. Indirectly, you can start entrepreneurship related to ISRO. They will always help you to do all these things. Anyway, you are now getting golden opportunity to get acquainted with ISRO team, so that you will get ABC of space program. That is enough. Being a beginner, especially in UG course, this will help you a lot in the future programs. I extend all my help, and I extend my sincere that wishes for you to come up, and this will definitely give you better opportunity in your future. I extend my sincere gratitude to all the faculty members of physics to go ahead with all this program, and thank you very much. Thank you.
Now I requested Dr. B.R. Manjunath, Head of the Department of Chemistry, to bless us.
Respected and dear Principal Sir, friends on the dais, and off the dais, my dear students. India, when you look at India as one nation, was talked about for quite, say, for more than quarter century as an IT superpower. In the information technology sector, India was viewed as a superpower, thanks to many iconic companies in India, quite a few of them in South India. Now, India is an emerging space superpower this because at a fraction of a cost that other countries spend, Chandrayaan 3 was achieved. And recently, the chairman, Dr. Somanath, ISRO chairman, there is a very popular, highly forwarded video I had posted to Dr. Priya Bharali also, where he says the future man will live for 500 years without requiring body. Only brain is sufficient. It will be integrated with a robo. When the robo lands on moon, you will be given simulated feeling that you are also landing on moon kind of. So I mean, what we consider fiction, scientific fiction, is today being made a reality, scientific reality. So we live in an age where the unthinkable, the unachievable, what is thought unachievable, is sort of people are right there achieving it. Dreaming, they say, as I was yesterday saying in another function, is also a form of planning. And whatever you can imagine is real, basically. So India is gradually proving that in field after field. Well, the question remains why in such a huge country of continental dimensions, we don't have even a single Elon Musk. Dr. Gopinath was talking about space entrepreneurship. So he is the number one space entrepreneur in the world. Mr. Elon Musk, as all of you are familiar, the SpaceX, he sends spacecrafts into space as if we are just traveling to Telcheri or whatever, with the same kind of ease, with same kind of frequency. How? That their system has made it possible, their education system has made it possible, their socio-economic system has made it possible, their political system has made it possible. Well, in India we have everything, but then there is a missing link. That missing link, we hope some young budding scientists among you sitting here will identify and work to overcome. And maybe a future Elon Musk will live to see from among you here. Thank you. Wish you all the best.
You also come. Everybody. Priya, Priya.
Here I am handing over the institutional certificate to our principal. Now I request our principal to hand over certificates who completed successfully the program. Mr. Abhinand Krishna. Mr. Abhiram K. Mr. Ajal N. Anushka Saumya. Ashish Anil Kumar, Aisha Lasni, Deepta, Ganga, Ganga Arvi, Gopi Krishna, Fatimatul Romana, Muhammad Nahyan, Sanju Krishna, Sanika Neri, Sanika, Setuna, Sanjit M, Sanjit, Sharanya P, Srinanda M, Tejas Prabha, Now I request Dr. Priya Bharali to give a so he is our resource person. She is specialized in astrophysics. So she will give a talk on this space program. So I welcome her. So let us welcome her grandly.
Very good morning to all of you present here. Am I audible to all of you? Last.
No.
Am I audible?
No. It's completely.
On. Hello.
Yes, yes. Yeah, it's now okay.
A very good morning to all of you present here. Respected Principal Dr. C. Asif sir, uh, respected Dr. K. Gopinathan sir, Coordinator IQSCL MGGAC Mahe, respected Dr. Priya Bharali sir, Head of the Department of Chemistry, respected Shankaracharya sir, Head of the Department of Physics, all the staff members, all the faculty members present, all the staff members present, and my dear student. Uh, Today my talk is the title of my talk is Astronomy and Space Exploration. So here I would like to give you a brief idea about astronomy as well as space exploration. The aim of my talk basically intends to some equals coming. Some equals.
No. I have opened the.
Okay.
The YouTube video.
So my talk is basically intended to motivate you, all the students, to pursue astrophysics and the career in space exploration in future. So I will start. First of all, I will put the outline of my talk. I'll start with an introduction to astronomy, then stars, evolution of stars and their spectral study, then about planets. I will discuss about galaxies, then interstellar space, then we will discuss need for space exploration, then space exploration technology. It includes launching rockets, space probes, space missions, then my conclusion and references. So I will start my talk with this not so famous quote, which says, "I know the sky is not the limit because there are footprints on the moon, and I made some of them." And you know that this is the quote by Buzz Aldrin, who was the second human, who was a person to second human to set foot on the surface of moon after Neil Armstrong in the 21st July 1969. So whenever we talk about astronomy, this is a very beautiful picture of night sky. So whenever we talk about astronomy, the first thing that comes to our mind, irrespective of our background, whether we are a science person or we are non-science person, it is always the night sky. So astronomy dates back to the time when humans started looking at the sky with lots of curiosity. And night sky is the first ever thing in the universe that has motivated the mankind to explore the stars and beyond. So every one of us have in our lifetime has tried to look at the sky and wonder what is there beyond. And there was a time when humans started looking at the star and they also started drawing some patterns. You might be aware of it. If you look at the clear sky, you can draw some patterns, and they just wanted to explain that why these patterns are being formed. And you can see I will present some of the patterns. So this is a pattern of the Orion constellation. These patterns are basically called constellation. So I'll always suggest all of you or to look at the sky sometimes and draw this pattern, whether you can find it. These are basically found during winter sky, and this is also called Mriga in Sanskrit. Then another constellation is a Leo constellation. So this type of constellation it's a group of many stars. If you connect them, they form a shape. Similarly, there's another constellation that is called constellation Cygnus. So you can say that this constellation, the science related to constellation started even when the humans were not fully civilized. So, and this is the first ever thing or that formed the part of the study of astronomy. So if I go to the concept of astronomy, so I would like to say that astronomy is the study of everything in the universe beyond Earth's atmosphere. That includes objects we can see with our naked eyes, like the sun, the moon, the planets, and the stars in the sky. It also includes objects we can only see with telescopes or other instruments like the far away galaxies. And nowadays, the astronomy has been developed in such a way that it even includes the questions about things we can't even see with our eyes, like dark matter and dark energy. So, as I have already mentioned that astronomy is nothing but the study of stars, planets, galaxy, interstellar space and all. Let me start with the star. So, all of us may be aware of it. So, theoretically, if somebody asks you what is a star, we can define star as a luminous ball of gas, mostly hydrogen and helium, held together by its own gravity. Nuclear fusion reactions in its core support the star against the gravity and produce photons and heat as well as small amounts of heavier elements. The sun is the closest star to us, that means to the earth. Now, where do stars come from? So, we always look at the stars, twinkling stars, and we have many songs and many poems written on that. But this is a time where we need to go to the depth of the construction of the star, how they are formed, what is their composition, and what is their life cycle. So, this is the stage we should start exploring about it. So, stars are basically born as clumps within the gigantic gas clouds that collapse in on themselves. The cloud's material heats up as it falls inward under the force of its own gravity. When the gas reaches about 10 million Kelvin, this is a very important temperature for star formation. This is a 10 million Kelvin. So hydrogen nuclei begins to fuse into helium nuclide, and then the star is born. But then when the star is born, that is not the end of the story. This is a baby star. This is called basically the protostar. So when the baby star is born, then it is not fully grown. So it will produce more and more energy through nuclear fusion. And there are a tug of war between the inward gravitational pressure and outward radiation pressure will start. So energy from the nuclear fusion radiates outward from the center of the burgeoning star and gradually halts the gas clouds collapse. So after a certain time, a situation will reach where there will be a perfect balance between outward radiation pressure and inward gravitational pressure. So at that stage, the star will be a full-grown star that is no longer a baby star. So that is a full-grown star, and this stage, this star is said to be the main sequence star. So it is like our adulthood. So we say that humans are the most productive during his adulthood. So star is in the adulthood, and the star spends most of his lifetime, like 80% of his lifetime, in the main sequence stage. Now this is a very famous picture. This is called the picture of this pillars of creation. So this picture was taken 25 years back by Hubble Space Telescope. So this is the picture of an Eagle Nebula. So as I have mentioned, I will go back to my slide. So here I have mentioned that the stars are born as clumps within giant gas clouds. So this picture is nothing but the giant gas clouds. These are called giant molecular clouds, and composition is 99% hydrogen and only 1% will be dust. So this is called the famous picture of pillars of creation. And you might have heard about James Webb Telescope, Space Telescope. Have you heard about it? So this was now after 25 years, James Webb Telescope took the same picture, and now this is the situation. So this thing is the pillar kind of thing that you are seeing here are nothing but giant molecular clouds, and here this is a location where stars are formed, and this is the location where we have all the energy, because you know that on Earth we are surviving only because of the energy received from the sun. If stars are not there, we cannot survive on a planet. and the stars are basically born in such region. And this is not the only reason. We can have so many other nebulas, star forming regions in the whole universe, and it is much more to be explored. Now looking at the properties of a star. So whenever we say star, we always talk about a twinkling star. And if I ask you what is the color of a star, we basically call white color or bluish white or yellow color, right? We always imagine like that. So the interesting thing is that in astrophysics, the color it doesn't always represent the wavelength. In astrophysics, colors represents the temperature. So to give a very clear view, I have shown here some stars from hottest to coldest part. So you can see a blue star that is called Regal. Its temperature is 25,000 Kelvin. So this is the hottest star till date. Then you might have heard about Sirius B. This is the brightest star in the sky. So a brightest star in the sky. So the Sirius B is actually blue white in color, and the temperature corresponds to around 10,000 Kelvin. Then we have a yellow star. So do you have an example for a yellow star? Sun. So sun's uppermost surface has a temperature of 6,000 Kelvin. That is why at 6,000 Kelvin, if you convert it into wavelength, it will correspond to yellow color. Similarly, we have orange color star that is called Aldebaran. So that is around 4,000 Kelvin. And we have a red star that is an Antares. So this is the coldest star. So I would like to tell you here that the hottest star is basically the youngest star, and the red color star is actually near its death. The star is going to die. So, and when it is a yellow color star, so you can say that the star is a middle-aged star. So, looking at the color of the star, we can get to know the life of a star, at what stage it is, whether it is old or young, whether it is near its deathbed or not. So, we can identify all these things. Now, if I want to summarize, because of time constraint, I cannot explain each and every part of the star life cycle. So I would like to summarize it with this picture. So how a star is going to live its life depends on its mass, how massive it is. So as we have discussed, stars are formed in the giant molecular cloud, and the star reaches a stage where there is a perfect balance between outward radiation pressure and inward gravitational pull. And that stage is called main sequence stage. You can see that there is a yellow star that is an average star. So this is like our sun. So for an average star, whose mass is comparable to the sun, it will, towards the end of its life, it will become a red giant. And you know that during nuclear fusion, hydrogen is fused into helium, and further it may form higher elements like carbon, nitrogen, oxygen. So these elements are formed in the red giant stage, and after that, after billions and billions of years, the red giant will also shed its layers into the interstellar space, into the infinity, and it will be left with a planetary nebula. And again, after billions of years, the core of the star will be left out, and all the materials from the planetary nebula will be shaded, and we will be left with a white dwarf. So the transition from the average star, red giant, planetary nebula is a silent process. So our sun is going to die a silent death, and it is going to become a white dwarf. But if the star is a massive one, so you can see that a blue star, massive star, so it is much more heavier than sun, then it will become a red supergiant. And what is the difference between a red giant and a red supergiant? In red supergiant, obviously there is a difference of size, and more than that, there is a possibility that more heavier elements will be formed, even greater than that of carbon, nitrogen, and oxygen. And the elements may go up to iron, because you know that the iron is the most stable element, right? So after red giant stage, super red giant stage, under its own gravitational pressure, the whole red giant will be burst into the space, scattering all the heavy elements into the empty space, and this phenomenon is called supernova explosion. And after supernova explosion, the core of the star is left out in the space, empty space, and it can be two types. The core can be either a neutron star or it can be a black hole. So the condition for formation of a neutron star is set by Chandrasekhar limit. So the Chandrasekhar limit is that if any star mass is greater than 1.4 solar mass, there is a possibility of formation of either neutron star or a black hole. So for neutron star, the range is 1.4 to 3 solar mass. But if the star is greater than 3 solar mass, it will definitely become a black hole. So this is the life cycle of a star to summarize. Now you might be asking me that how do we get so much of information, because there is no chance that humans have visited those stars, right? It is not at all possible to visit the stars and gather the information from them. So this is a called an extreme form of remote sensing that exists in astrophysics, that is called spectroscopy, and specifically it is called stellar spectroscopy. So here I have put a very simple spectrum of a star. So to understand stellar spectroscopy, we need to understand about emission and absorption. Now in this picture, you can see that in the upper panel, I have represented just a picture of a spectrum, and it looks very nice with so many colors, red, yellow, green and blue. But you can see that the spectrum is not continuous, right? It is interrupted by some dark lines. Okay, so the same picture of the spectrum, now it has been spread out to a graph of a spectrum in the lower panel, and you can see the colored continuum basically represents because of the emission, and the dark notch or the deep places, dark lines that you can see, this is because of the absorption. Now who does the absorption and emission? The elements present in the star does the absorption and emission process. You know that if an electron absorbs an energy and goes to an excited state, then excited state is an unstable state, right? So it will always want to come back to the ground state. So when the electron jumps from the higher excited to the ground state, the difference of energy is emitted, and this is called emission energy. So on the other hand, if an electron absorbs some amount of energy to the ground state, the difference of energy is called absorption. So here, at what wavelength these dark lines will appear will solely depend on the atomic number of the element who is doing the absorption or emission. Now, if you can find out at what wavelength the dark deep notch is appearing, you can find out the Z, that is the atomic number. So this is what astronomers do. Astronomers basically find the detailed spectrum of a star, and they find out various wavelengths at which absorption and emission lines are appearing. And remember that this spectrum is like fingerprint. Like no two fingerprints can be similar, no two spectrum can be similar. So each and every star has its own spectrum, and each and every star gives a detailed view of what are the elements present there. So just to say about emission. So what is an emission spectrum? When energy is absorbed by electrons of an atom, electrons move from lower energy level to higher energy levels. These excited electrons have to radiate energy to return to ground states from the excited state, which is unstable. The emission spectrum is formed by the frequencies of this emitted light. On the other hand, an absorption spectrum is constituted by the frequencies of light transmitted with dark bands when energy is absorbed by electrons in the ground state to reach the higher energy state. So emission and absorption line present in the spectrum depend on the orbital structure of the electrons in atom. And orbital structure is again dependent on the atomic number. Now, this is just a comparison. When element in ideal conditions should exactly resemble a black body. Okay, so the emission coming from a star should be exactly similar, should be explained well by black body radiation. That is called Planck function. So on this side, on the left panel, you can see an ideal thermal spectrum. But in reality, nothing is ideal. So the actual stellar spectrum looks like this, the right panel that you can see on your right. So in that picture also you can see that instead of being an ideal black body spectrum, it is carrying so many peaks as well as so many dark lines. So the location where these peaks and the dark lines appear can give you information about the element responsible for these dark lines or the peaks. So scientists use spectroscope in a telescope to break the spectrum of stars into their component colors to find the elements present. Another thing that we should be thinking is that whenever we talk about stars, we always say that this is the temperature 6000 Kelvin, 7000 Kelvin, 25,000 Kelvin in one of the slides I have shown you. So now the question is, how do we exactly find out the temperature? Is it really possible to put a thermometer there and check the temperature? It is not at all possible, right? So this is also another kind of remote sensing. So in this case, we take the help of Wien's displacement law of black body radiation. So in this picture, in the bottom that picture you can see, so according to Wien's displacement law, the wavelength at which the energy distribution for black body radiation peaks is always inversely proportional to the temperature. So the product of lambda peak into T will always be a constant, and this is given by 2.898 into 10 to the power minus 3 meter into Kelvin. So now look at this diagram on the other side. So you have this is a stellar spectra. It's a normal star spectra you have collected. So what you need to do, you need to see the peak. So you can see a red line. So the red line basically represents the peak of the spectra. Now you find out the wavelength belonging to the red line. So if you find out the lambda peak, you can tell what is the temperature of that particular star. So there I have tried to show one simple calculation with lambda peak equal to 4580 angstrom. So using Wien's displacement law, we have found that T is equal to 6300 Kelvin. But interesting thing is that all the stars are not alone. Okay, in our space, where whatever stars are there, stars are never alone because stars have huge gravitational impact. So gravity always asks for other masses to combine. So since all the stars have their own angular momentum, say they will not exactly combine, but they will form a binary system and they will start rotating about a certain center of mass. So this is called, so binary system can be of many types. In a binary system, there may be two stars, normal star means full grown star, there may be one normal star, there may be one black hole, then another binary, there may be a black hole and one normal star with a neutral star. So this is one binary where we have a normal star along with a black hole. So you can see that the material from the star is being accreted towards the black hole and some jets are being emitted perpendicular to it. So this is a very common phenomena in the outer space. Now when the star is in the company of another star or another compact object, then what will happen? So will the spectrum be same? No. So these are the two examples of the spectra that I have taken from two of my papers which got published back in 2019. So this is a binary system. First picture, the upper picture, is of a binary system where one is a normal star and another is a black hole. Now you can see in this picture, you can see the dark patches. Can you see the dark lines, black lines, and blue lines? So the black lines are exactly resembling a Planck function, right? So that is a thermal spectra, and the blue lines are because of the non-thermal emission. Similarly, in the second photo graph also you can see that the spectrum is not that simple like we had for the single star. So here also we had a thermal component along with non-thermal component. When we say thermal component, it is exactly explained by a black body radiation function, like Planck function. But here we have not only thermal component, we have non-thermal component. So this is the spectrum of a star when it comes into the company with other stars. So what we can do from here? So this is another branch of astronomy where you can do astrophysical spectroscopy to study the spectrum to find out what is the ratio of thermal component, what is the ratio of non-thermal component, and from that idea you can give us an idea about the stellar environment. What is the geometry of the star? What is the geometry of the environment around the black hole? Maybe a neutron star. So these are some of the applications of stellar spectroscopy. So I will not go into details of stellar classification. These are available in all the books, textbooks we have. So what I want to say that there are basically 7 classes of stars, and how they are divided. They are divided on the basis of their temperature as well as the signature emission lines and absorption line present. So you can have a very detailed view of how the stellar classes are varying. So it is O, B, A, F, G, K, N star, and our sun belongs to G category. And you can have a very detailed idea how stellar classification is a different chapter. So I will not go into the detail of stellar classification. Now about the galaxies. Now when we know about the stars and how the stars are formed and developed, their evolution is going on. And we have also come to know about some idea about how the star is going to die. Now, galaxy is nothing but a large group of stars, gas and dust held together by gravity. There are 3 main types of galaxies. One is called lenticular, then elliptical and spiral galaxy. There are at least 18 billion, remember it is 18 billion galaxies in the universe. These are the picture of types of galaxy. You can have a better idea about it. So you can see the first one is called barred spiral. So next is called irregular, when you cannot define any shape. Then it is exactly a spiral. Then we have peculiar galaxy. That means these galaxies do not fall into some category. Then we have an elliptical galaxy, and then we have lenticular galaxy. Lenticular galaxy is nothing but a fusion between spiral and elliptical. When a spiral galaxy and elliptical galaxy collide with each other, then it turns into the formation of a lenticular galaxy. So there is also a very broad classification of galaxies, and for this Hubble gave a law that is called Hubble's tuning fork diagram. So you can see that it is the whole classification is formed in the form of a tuning fork. It starts with E0, E3, E5 and E7, and S0 is nothing but the lenticular galaxy. That means the fusion between spiral and elliptical. Interestingly, our own galaxy is a barred spiral galaxy. So in addition to spiral, we have a bar at the center. Now, we have come to an age that if I ask you, what is your address? So usually we say that house number, island number, road number, like post office, we say district, then country, and the zip code or pin code. Now, here at this position, if I ask you what is your cosmic address, what should be your answer? Can you identify this diagram? So this is our Milky Way galaxy. But is it really the address? Is it the precise address? So let us just zoom into that. Now we are just having a top view of our Milky Way galaxy, and you can see where is our sun. The point from which the red circle is originating is our sun. Now let us have a very side view of our galaxy. Now our Milky Way galaxy has 5 major arms. One is called Norma arm, then is called Crux Scutum arm, Then we have Perseus arm, we have a Carina Sagittarius arm, and Cygnus arm. And you will be surprised to know that if you consider these arms as a highway, Earth, the solar system, our solar system is not even on highway. We are on a bilane. Okay, so that is a local arm of our solar system that is called Orion arm. So we are actually on a small local arm. Now let us just zoom much more into that. So we are inside our solar system where we are going around the sun. So if I ask you, what is our cosmic address? So we will start like seminar hall, MGGAC. No. If we say New Mahe, Puducherry, that is also not the correct answer. So let us move out like Asia, Northern Hemisphere, the Earth. Then we have a solar system with the sun. Then we are on the Orion arm, which is nothing but like a bilane in our galaxy. Then we are on a Milky Way galaxy, which is not even a single galaxy. This is a part of a local cluster. Okay, so there are 80 billion galaxies in the universe, and our galaxy is a part of a local cluster. And then the universe, and there may be something beyond. Who knows? So to sum it, so if we talk about this cosmic address, the Earth is the third planet from the Sun. The Sun is one of the 100 billion star systems in the Milky Way. The Milky Way is one of the 40 galaxies in the local group, and the local group is a part of local supercluster, which is a part of the universe. Now everything in the space is moving all the time. You might feel like you are sitting still, but actually you are flying through the space incredibly fast. That is because Earth is carrying you like a spaceship. Earth is spinning. Earth is also orbiting around the sun, moving even faster. The speed is 67,000 miles per hour. The sun itself is moving around the center of our galaxy, carrying everything in the solar system along with it at the rate of 4,90,000 miles per hour. And that's not all. Our galaxy, the Milky Way, is moving too at the rate of 8,72,405 miles per hour. And our cluster of galaxies is also moving, and so is everything else in the universe. So this is an artistic simulation of our solar system. The yellow ball that you can see is actually our sun, and the whole solar system is in motion. We are not static, we are moving. And then the solar system, galaxy in which we are sitting, that is also moving, and the supercluster of which we form a part is also moving. Now, what is a planet? When it comes to asking what is a planet, we usually say a planet is a large object that orbits a star, but it is not yet complete. There are so many theories put forward to explain a planet and how theories related to the origination of planet. So the more we learn, the more it changes. Scientists believe planets begin to form when a dense cloud of dust and gas called a nebula spins around a newly formed star. Gradually, the gravity causes the bits of matter in the nebula to clump together. Slowly, these clumps accumulate and grow, and eventually, these clumps become planets. The most recent definition of a planet was adopted by International Astronomical Unit in 2006. It says that planet must do three things. It must orbit a star. It must be big enough to have a gravity to force it into a spherical shape, and it must be big enough that its gravity cleared away any object of similar size near its orbit around the sun. Discussion, debate will continue as our view of cosmos continues to expand. Now, somewhere you might have seen there is no planet B, right? So we don't have but nowadays this is not true. We may have a planet B, and many because of global warming and many other issues, it is said that Earth may no longer be suitable for human living in future. So there are plans to colonization of humans in other planets. So this project is called Search for Habitable Zone or Goldilocks Zone. So according to this, a habitable zone is the area around the star where it is not too hot or not too cold for liquid water to exist on the surface of surrounding planets. A habitable planet should orbit a star which should remain stable in the output for billions of years. A habitable planet must have an almost circular orbit so that constant condition for sustaining life can prevail. It should not orbit a star which is very close to cosmic explosion like supernova. It should also be far away from massive planets which can continuously direct asteroids towards it or perturb its orbit. So this is an artistic impression for habitable zone. The green plan strip is showing the habitable zone where it is not too hot or not neither too hot or not too cold. So just right temperature. So these are some of the habitable worlds we have found. Then about interstellar space, between stars, planets, and different galaxies, we have whatever we have is called interstellar space, and it is not empty. It is far, far away from empty. Interstellar space basically carries neutrinos, charged particles, atoms, molecules, dark matter, photons, ranging from the highest energy radiation to the sluggish light of cosmic microwave background. So, which is cosmic microwave background is considered to be one of the remnant radiation from Big Bang. The interstellar matter is mostly composed of atoms of hydrogen, that is 90%, and helium 8%. Apart from that, we can have so many heavier elements, and the stars are going and more towards evolution. We may have more and more heavier elements in interstellar space. Now, space exploration. Space exploration is the discovery and exploration of the outer space by means of space technology. Physical exploration of the space is conducted both by human spacecraft flights or by robotic spacecrafts. Now, space exploration is for space exploration, we need space technology. Space technology is a technology that is related to entering and retrieving objects or life forms from the space. Everyday technologies such as weather, forecasting, remote sensing, GPS system, satellite television, some long distance communication system critically rely on space infrastructure. Now you know that we can our aim for space exploration only when we look beyond the Earth's atmosphere. Now to look beyond Earth's atmosphere, we have two ways. One way is that we can put some observers in the orbit outside Earth, or we can send or launch space probes into the deep space to explore it. So the space exploration started many years back by setting up space observatories. Now, what is the reason for putting space observatories? Because you know that over the electromagnetic spectrum, all the radiation cannot penetrate Earth, right? Earth's atmosphere. Like gamma ray, X-ray, UV, infrared, and part of microwave, they cannot enter the atmosphere of Earth. So if you want to, but most of the radiation coming from the outer space is in X-ray, gamma ray. So if you want to have a clear idea of what is happening outside, we must place observer in the orbit above the Earth's atmosphere. So these observers are called space observatories, which are the device launched into the orbit of Earth for observing distant heavenly bodies like stars, planets, etc. So these are some of the famous space observatory. The first one is called NuSTAR, that is Nuclear Spectroscopic Telescope Array, which is a NASA space-based X-ray telescope to focus high-energy X-ray from astrophysical sources, especially for the nuclear spectroscopy, and operates in the range of 3 to 79 kiloelectron volt. And there is another observatory in the International Space Center that is called Monitor of All Sky X-ray Image. That is shortly called, in short, it's called MAXI. And this is basically devised by some Japanese experiment. And this is a space observatory by India. You might be aware of it. This is the AstroSat, which is India's first ever multi-wavelength space observatory. Why is it called multi-wavelength? Because it can observe on various wavelengths on the electromagnetic spectrum, like X-ray, gamma ray, UV. So, and till now, as far as I know, around 3 Nature papers have been published on the results from AstroSat. So this is a great achievement for our country as well as ISRO. And this particular observatory is still in the sky and observing, but there is a plan to launch another version or second version of this launch, because most of the detectors unfortunately has stopped working, and UV, that is the UV detector, is still working. And we hope that we will have more contribution towards the space observatory by ISRO. So when we talk about the space observatories, who will put the space observatories in the orbit? So there we need a vehicle. So that is nothing but our rockets. So rocket is a space vehicle used to transport missiles and satellites into the space or between the orbits. So it basically works on the simple principle, that is Newton's third law of motion. So here the main thing that plays a great role in a rocket movement is the propulsion. All spacecraft need to reach about 17,500 miles per hour to get into the orbit. Thrust is used to push the spacecraft this fast. Thrust is produced by burning a rocket fuel and oxygen. If there is not enough thrust, the spacecraft will fall back to Earth due to gravity. So this is a simple mathematics involved for satellite launch by vehicles. So all of us know the orbital velocity is given by square root of G, capital M by R. Similarly, escape velocity is square root of 2G M by R. We have already studied those things in our school's curriculum. So condition for launching artificial satellite is that if the velocity is exactly equal to orbital velocity, then the satellite goes in a circular orbit. If the velocity is greater than orbital velocity but less than escape velocity, then the satellite goes in an elliptical orbit. If the velocity is greater than escape velocity, then the satellite takes a parabolic path and escapes into infinity. And the fourth condition is if the velocity is greater than escape velocity, the satellite takes a hyperbolic path and escapes into the infinity. So you know that Aditya L1 was launched, and this formula, this equation, these conditions plays a great role in deciding the trajectory of the objects or the probes that we are throwing into the space. So this is a very ideal rocket equation. So I have taken it from the NASA website. So we know that if you want to reach the low Earth orbit of Earth, we need to reach a velocity of 17,500 miles per hour. So here you can see in the red box, it is del U is equal to V equivalent ln mf by me, where mf is the mass of the fuel and me is the mass of the empty rocket. So if you decide the velocity required to put the satellite in the orbit, you can decide how much fuel is required to put it there. So this equation plays a great role in putting the satellite into the orbit using a rocket. So these are three different types of Earth orbit. One is called low Earth orbit, which is in between 500 to 1000 kilometer. Then we have a medium Earth orbit, which is between 5000 to 15,000 kilometers. And then we have geostationary Earth orbit, which is at the height of 36,000 kilometers above the surface of Earth. So our International Space Station is in the low Earth orbit, and it can also change its orbits, like inclined orbit, polar orbit, or equatorial orbit with the passage of time. So these are the total number of satellites on space, and now this is how Earth looks from outer space. So at present, there are 5,500 satellites in the space, and by 2030 it is expected to grow to 58,000. Around 42 countries have put their satellites in the in the Earth's orbit, and this is a picture we have from the outer space of Earth. So I have skipped most of the parts, like many space missions are there. So this is one of the mission that is very recent one, that is Aditya L1 mission by ISRO. This is one of the space probe which is sent to the towards the sun by ISRO, and it aims to study the dynamic nature of sun's outermost layer, corona, and the chromosphere, and to collect data about the coronal mass ejection. It is also aimed to study the solar storm and their path through the interplanetary space from the sun to Earth. So, pros of space exploration. Space exploration has the potential of discovering the yet undiscovered facts about the space. It may bring about a dramatic change in our lives. Through the exploration of space, we may find new materials, new precious materials. Apart from that, we have so many, it may also enhance our communication system, television channels, internet services, and space exploration also gives us a very precious gift that is called spin-off technology. So spin-off technology is, these are the technology which were developed during the space probe or space shuttle launch, and nowadays this same technology is used for kidney dialysis and the new artificial heart that have been based on a technology found in the space shuttle. Programmable heart pacemakers were first developed in 1970s using NASA satellite electrical system. Apart from that, image processing used in CAT scanners and MRI technology in hospital worldwide came from the technology developed through computer pictures of the moon for the Apollo programs. Joystick evolved from Apollo lunar rover used for computer games, cranes, mining trucks, underwater unmanned vehicles. So with this, I will conclude. Space exploration is the key to the future, and we will reap the rewards of the necessary investment of money and resources. Researchers and technologies about the space exploration are very important for humanity. Without risk, we remain in our caves, never daring to see what lies beyond our immediate sight. The money we are spending now on space program will help in the long run, and it is the main thrust of humanity's future dreams, which expands their limits as new projects accomplish. These are my references. Thank you.
Good afternoon, everyone. I'm Aisha Nesmi of third year BSc Physics. It gives me an immense pleasure to deliver the vote of thanks for this event to all the dignitaries assembled over here. First of all, I would like to thank our beloved principal, Dr. C. A. Asif sir, who honored this function with his inspirational thoughts. I would also like to thank Honorable Dr. K. M. Govinath sir, coordinator of IQAC cell, MGGAC Mahe, and Mr. A. Sajay Kumar, superintendent, for being a part of this. I also thank Mr. M.G. Shangaracharyu, HOD Physics, MGGAC Mahe. I also like to thank Dr. Manjunath sir, HOD of Chemistry, HOD Maths, thank you ma'am for being a part of this. Also thank you Sandeep sir and Sari sir for this part. And next, I need to mention my deepest sense of appreciation to our beloved Priya ma'am, that is our Dr. Priya Bharali, Assistant Professor of Physics, for taking all the efforts for this program. Thank you ma'am. I would also like to thank all the staff members, students, participants, and last but not least, our beloved audience for making this function to be a great success. Again, thank you everyone for being a part of this. Thank you.
Live streaming. Our classroom. I need to switch it up. I need to finish that.
We just start their come.
Okay.
They just off of the.
I will.
Yeah.